Here are the example solutions for examples 39 to 45 on the two power equations using P equals V squared divided by R and P equals I squared R. So we'll start off with example 39, and we have a heater, 2.5 kilowatts power and 100 ohm resistance. The first thing to do is to start writing down the information that you've been given. So we have power equals 2.5 kilowatts, resistance equals 100 ohms, and then we're trying to find the current. So we can write the equation P equals I squared R and then substitute in different quantities that we have. On the left we have P, that's 2,500 watts, and we also have R on the right, 100. So that gives us 2,500 equals I squared times 100. Now we need to find I squared and then we need to find I. So to find I squared, we can divide both sides of the equation by 100, and that will give us I squared equals 25. Square root both sides of this to get I equals 5, and then remember that you need to include a unit, which is the amp. Next example, example 40. This time we have a wire with a resistance of 6 ohms and a current 2 amps, and we're asked to calculate the power. So again, this is a multiple choice one, but we will, for the purposes of this exercise, we'll write down the different quantities that we've got formally. So we have the resistance 6 ohms and the current 2 amps. We're trying to calculate the power. Again, P equals I squared R, so we substitute in 2 for the current, but it has to be squared, 2 squared. Times that by 6, so that's 4 times 6, 24 watts. Example 41. So this time we have transmission lines which are taking electricity to a remote community. And the current in the transmission lines is 200 milliamps, a total resistance of 20 ohms. So calculate the power loss in the transmission lines. Now the power loss is just the power, it's the power developed in the transmission lines, P equals I squared R. The current is 200 milliamps and the resistance is 20. Now 200 milliamps, a milliamp is quite a small unit, 200 times 10 to the power of minus 3. So if you wanted to enter that on the calculator, it would be 200, and then milliamps, use the scientific notation button. And then minus, use that minus key up there, 200 times 10 to the power of minus 3, which is 0.2. That has to be fed into P equals I squared R. So the equation becomes 0.2 squared times by 20. So 0.2 squared times by 20 is 0.8, and then the unit being the watt. So that's that one. Now the next one is example 42. So we have this circuit here, 12 volt power supply, a 100 kilo ohm resistance. The power supplied to the resistor. Again, multiple choice, but we'll go through the workings. So I've written down the voltage, 12.0 volts and 100,000 ohms, 100 kilo ohms, or 100 times 10 to the power of 3. So this time, the equation that you're going to need is P equals V squared divided by R. So P equals V squared divided by R is 12.0 squared, and then divided by 100 kilo ohms, and that's 100 times 10 to the power of 3. That looks like a bit like a 7, but it's meant to be a 3. So 12.0 squared divided by 100 times 10 to the power of 3. So I'm using that scientific notation button again, and that gives me 1.44 times 10 to the power of minus 3 watts, which is option B. Moving on to example 43. Calculate the resistance of a device with a power rating of 550 watts when operating at a voltage of 10 volts. So write down the information we've been given. P equals 550 watts, voltage 10 volts. We're trying to calculate R. Now that means we can use P equals V squared divided by R. So let's substitute in the values we've been given. So P 550 on the left, and then voltage 10 squared divided by an unknown resistance. So to rearrange this equation, we're looking at cross multiplication. So you're going to swap the 550, which is on the left side of the equation, with the R, which is on the bottom of a fraction on the right. And that will give you R equals 10 squared divided by 550. So let's have a look at what that calculation comes out as. When I do 10 squared, which is obviously 100, 10 squared divided by 550, I get 0.1818 as a decimal. It goes on for quite a while. But I should only be working with probably two significant figures. And so I need to round it to two significant figures here, 0.18 in there. And the unit is the ohm. Okay, next one. The loudspeaker in a bank alarm has a resistance of 48 ohms and a power of 3 watts. Calculate the voltage. So 48 ohms, 3.0 watts, and this time again P equals V squared over R. Substituting in the values, so on the left 3.0 watts and V squared divided by 48. This is a bit of an easier one to rearrange. The way to get V squared is simply to multiply both sides of the equation by 48. So it's 3.0 squared multiplied by 48. That will give you V squared, which you then have to square root. So we can do 3.0 squared times that by 48, get that as an answer, and then square root that answer. Is 20.78. Which is 20.8 volts, or 21 volts to two significant figures. Alternatively, you can just square root 3.0 squared multiplied by 48, and you'll get the same answer. Right, this is the last question. So example 45. You start with a resistor which is labelled 10 ohms, plus or minus 10%, and 3 watts. Now what that actually means is that the true resistance could be between 9 and 11. So 10% of 10 ohms is 1 ohm. So it could be 1 ohm above or below 10. A student decides to check the value of the resistance. Draw a circuit diagram including a 6-volt battery, voltmeter and ammeter for a circuit that could be used to determine the resistance. Now this is basically straight out of your notes on Ohm's law. So we need the battery, 6 volts, an ammeter in series with the resistor, and then a voltmeter connected across the terminals of the resistor. That's your circuit diagram. Next part is asking you to calculate the resistance, again just using Ohm's law. So we've got V equals 5.7 volts, I equals 0.6 amps, R equals V divided by I, which gives us 9.5 ohms. Nothing complicated there. On to part C. During the experiment, the resistor becomes very hot and gives off smoke. Explain why this happens. You must include a calculation. So if something becomes hot, then that's a clue, because that requires heat energy. And energy divided by time will give you power. So if we calculate the power, then that would give us an idea of how much heat energy might be dissipated in the resistor. So we're going to calculate the power using P equals I squared R, or we could use P equals V squared divided by R. But I'll use P equals I squared R. So I have given to me, using the numbers that are supplied for the actual experiment, 0.6 amps and 9.5 ohms. That gives me 3.4 watts. Now again, I've rounded that to two significant figures. 0.6 squared multiplied by 9.5 is 3.42. There's no point keeping the extra 100th there. We'll just round that to the nearest tenth. 3.4 watts. So the question asks you to explain. I've got my calculation, so my explanation would be that the heat builds up since 3.4 joules of heat are produced every second. So remember that 1 watt is the same as 1 joule per second. And that's your definition of power. Power equals energy divided by time. Okay, next final part here. Student states that 2 of these resistors would not have overheated if they were connected in parallel. Is this correct? So what they're thinking is if you connected them in parallel, then parallel combined resistance would be less. So is the student correct? Well, we can calculate the power of one of these resistors using P equals V squared over R. Now if they're connected in parallel with the battery, then each resistor will still obtain the full battery voltage, which is 5.7 volts from part B. So you've got 5.7 volts and 2 of these resistors, so each resistor is still 9.5 ohms. So you're going to have P equals V squared divided by R, which is going to give you 5.7 squared divided by 9.5, and that's going to be the exact same value as you got in part C. 5.7 squared divided by 9.5, and you could have used that formula in part C and you get 3.4 watts again. So the student is wrong, since each resistor in parallel has a voltage of 5.7 volts across it and the power is the same as before.